Okay, so we're going to talk about hypothesis testing in this lecture, and we're going to focus on one sample tests. We're going to talk about the first two topics here, elements of a statistical test and large sample statistical tests. The rest of these we'll cover them in future videos. So what are the elements, or what is a statistical test? A statistical test is a choice between alternatives. So you're going to pick one alternative versus another of a parameter, and you're going to base that on data, on statistical data. So typically one of the parameters we are interested in is the population mean. So we want to find out, since it's unknown, whether it's larger than a certain value or less than a certain value. So for that, the first two elements of a test are called the null hypothesis and the alternative, or the research hypothesis. And we write that H sub 0. We write this as H sub A. That's the alternative. This is the hypothesis we want to prove, and that's the status quo. Okay? So to make a choice between these, we collect data, we summarize the data, and we call that data summary the test statistic. So that's how we summarize our data, using the test statistic. And then, so what do we do with this? We then create a rejection region. I'll show you that in a minute. And so we reject H0 if this data falls in one place, and we don't reject if it falls in another place. So our decision would be either to reject H0 or do not reject H0. And notice we use do not reject, we don't say accept. We'll talk about that later. And then we have the conclusion, which is the stating the decision in a more layman terms so people can understand it, and say we usually have a significance level alpha. Remember, alpha is the probability of making an error. So whether we have sufficient statistical data to favor the alternative or not to favor it, so we have to say that. Okay. So what's let's show graphically about the rejection region. So here's what we have. So I just have this graph here, and so because once we summarize our data, it's going to be a z value, and we create this bell shape, and we have these two critical values in this case, and from this point on, that's called the rejection region, RR, rejection region. And from this point and below that, that's called another rejection region. And in between, we don't reject, so we call that non-rejection region. So once I calculate my data summary, if it falls up there above this value, then I say reject H0. If it's here, I say reject H0. If the value falls anywhere here in between, I say do not reject H0. So that's how the rejection works. And we have to keep in mind that in this case, H0 represents the status quo. The alternative represents the hypothesis that we want to provide evidence to justify. Typically, we state what we want proof under the alternative. And we show the idea of this testing hypothesis is we try to show that HA is true by showing H0 is false, cannot be true. That's like a proof by contradiction. Since this can be true, then this have to be true. Of course, in doing so, because I have these two hypotheses, and one of them has to be valid, one is not, it's possible my data will indicate one is true while in reality the other one is true. So that gives rise to errors, and two types of errors, type 1 error and type 2 error. And type 1 error occurs when if it's because I don't know what mu is, so it's an unknown parameter. I'm trying to find out what its value based on data, so I can sometimes I'll make the mistake of misjudge the value. And sometimes if the value, if H0 is true, if the hypothesis is true, but I end up rejecting it, that's called a type 1 error. If H0 is false, I end up not rejecting it, means accepting a false hypothesis. That's called type 2 error. Okay, and these have probabilities of occurring, depends on my data, its sample, how large it is. And alpha is called the probability of type 1 error, so this is called alpha. And beta is called the probability of type 2 error. Sometimes what we do usually, alpha is more serious than beta. So I fix alpha at 5%, the default value. Sometimes I pick alpha at 10%, sometimes 1%, depends on how serious that error is. And let beta be whatever it is. But if I let beta flow, it can be large. So we're going to define this 1 minus beta, which is rejecting H0 when it is false, which is something we'd like to do, to be the power of the test. So that's called the power of a statistical test, is 1 minus beta. Of course, here we dealt with the other two situations, is to accept H0 when it's true, and that's a correct decision, or to reject H0 when it is false, and that's also the correct decision. So these four situations lead to 2 correct decisions and 2 incorrect decisions. One of them is here the type 1 error, and the other one is type 2 error. And I said type 1 error is much more serious than type 2 error. So I want to illustrate that in non-statistical examples. So I would just give you a sense why we consider type 1 error to be more serious. So here's an example where, say, in a court case, usually the status quo that is everybody is innocent until proven guilty. You know that principle. So the status quo H0 would be innocent, and the alternative is guilty. So if you take someone to court, you want to prove them guilty, and that makes sense. So you have the burden of proof, and typically you want to prove them guilty. That's hard. So you just try to say they cannot be innocent. So prove by contradiction. And so if let's see what would type 1 error mean. So if H0 is true, so the person is innocent, but the judge ends up rejecting that and saying the person is guilty. So that would be sending an innocent person to jail. That's alpha. That's the first type of error. The second type of error a judge would make is if H0 is false, if the person is guilty and the judge makes the decision that the person is not guilty. Say, judges never say the person is innocent, they say not guilty, but that's letting a guilty person go free. And so in our court system, it's much more serious to send an innocent person to jail than to let a guilty person go free. Both are not desirable, but this is much worse if you make that mistake. So that's why we make alpha very small, and sometimes guilty people go free, because in our system we want to make sure that only the guilty go to jail, and we don't want to send innocent people to jail. Okay. Another example where, so if you have drug company wants to sell drugs, and so they come up with this new drug, and they have the burden of proving it satisfies or it heals a certain condition. So they want to prove to the FDA that the drug is acceptable. So the status quo, if somebody comes with you with a new drug, you say no, it's not good until you show me otherwise. So you set up this problem as the new drug is not acceptable, the new drug is acceptable for the alternative. And in this case, again, if we go to the hypothesis test, type 1 error is to reject H0 when it is true. So if H0 is true, the drug is not acceptable, but you say it's good, that means marketing a bad drug. So because you're going to sell that drug when it in reality is not good. While if it turned out to be the drug is acceptable and you decide it's not, then you're going to end up not marketing a good product. Of course, if you look at the error, the beta error, not marketing and accept a good drug, that's a loss of money, opportunities to sell a good drug because you made the wrong decision in your statistical analysis. But if you look at the other possible error, marketing a bad drug, there's going to be side effects and lawsuits, so that's going to mean your company will be ruined. So it's much more serious, and you want to limit this to be as small as possible at the expense of maybe having to lose a market opportunity. You can lower both of them by picking a large sample. Spending more money means you can control both of these errors. So here is the large sample test. I'm going to go over this quickly and then go to a real example. So any parameters we are interested in are either mu, p, mu1 minus mu2, p1 minus p2. We call them theta. And in all cases, we need sample data, we need the sample size, we need an estimate of the parameter, and we need its standard error. So we need to set up these hypotheses, and we're going to set whatever parameter we choose from here to be equal to some value theta 0. And the alternative would be, it's going to be either theta greater than theta 0. That would be one problem. Another problem would be theta less than theta 0. A third problem would be theta is not equal to theta 0. Okay? And so the test statistic in this, if I take the point estimate, subtract this right hand value, divide by the standard error of theta hat, that will be a z, because we've seen that like x bar minus the mean of it over the standard deviation is the z-score, provided my sample is large. And then I want to get a critical value, z alpha, if I'm dealing with a one-tail test. This would be z alpha. I would get it's negative if it's lower tail, or z alpha over 2 if it's a two-tail test. So again, this would give me an upper tail test. This is a lower tail test, and this is a two-tail test. And then my rejection region would be reject H0 if z is greater than z alpha, reject H0 if z less than negative z alpha in the second case, and reject H0 if z is greater than z alpha over 2 or less than negative z alpha over 2 in the third case for two-tail tests. And then I check this observed value. If it's in the rejection region, if it's larger than z alpha, I reject H0. If not, I do not reject H0. And the same thing in each case. And we've seen that here in this graph. So that's what I have here. So this is for this example. Let me see if I can write. So this is a situation where I have H0 is theta equal theta 0, and the alternative is theta is not equal to theta 0. So in this case, I compute my test statistic value z. If it's here, I say reject H0. If it's here, I say reject H0. If it's here, I say do not reject H0. If my alternative is theta greater than theta 0, then instead of this z alpha over 2, I'm going to have only z alpha, and I don't have anything there, and my rejection region would be up here, and everything else below it would be my non-rejection region. So if my 0 falls up there, I would reject H0. If it falls below that, I would say do not reject H0. The same thing if my theta is less than theta 0, then I would get my critical value would be negative z alpha. I would be below here, and this would be my rejection region, and I would reject if my test statistic value z is down here, and I do not reject if it's up there. Okay, so this is how the test is structured, and in next we're gonna talk about applying it to the population mean. All right, thank you.